Alright, so to begin with our review of energy and momentum, let's start out with a basic definition of energy. What we've always said is energy is the ability of an object to change itself or the world around it. And there were a few different types of energy we talked about. The first was kinetic energy, which is the energy of movement. Okay, we can find that with K equals 1/2 mv squared. We had gravitational potential energy, which is the energy associated with height. And for that we have Ug equals mgh. And we have spring potential energy, which is the energy stored in a spring. And for that we have Us equals 1/2 kx squared. Alright, moving on to work. Work is the change in energy that results from a force being exerted over a distance. Okay. Alright, we have three ways to find work. The first is that work is simply the change in energy, and that really just goes back to our original definition. The second is finding work from a force, F delta x cosine of theta. And the third is we can find the area, okay, on a force versus position graph. That essentially means we're multiplying force and displacement, and that's going to lead to work as well. Just a few quick notes about these situations where work is 0, right? We know that if our angle is 0, we have no work done, or if our displacement is 0. Also, there's no force, but that one's a pretty obvious one. But those two, we need an angle other than 90, and we need an actual displacement to lead to work. Heat, just real quick as an idea, this is a simplified version, but heat is the energy loss due to friction. Okay, there is a more complicated definition of it, but we're not going to worry about that for now. That's all we need to know for our purposes. Alright, conservation of energy. The basic idea is that the total energy in the universe is constant. And that goes back to the idea that energy can't be created nor destroyed. However, if we're looking at individual objects, we can have changes in the energy of individual objects in two situations. One is energy is changing forms, but the total is the same. All right, so this would be kinetic becoming potential, potential becoming kinetic, things like that. Or we could have work being done. All right, in that case, the total changes and energy is transferred from one object to another. So work really gives us a mechanism for energy to be transferred from one object to another. Our formula, the thing that we went back to many times, is the initial plus work done by non-conservative forces is equal to E final. Just a quick note about that. Our two major non-conservative forces that we talked about were friction and pushes or pulls. Okay, gravity, springs, these are going to be conservative forces. All right, so we don't need to worry about the work done by them. We instead worry about the potential energy that results from them. All right, so we have spring potential energy, we have gravitational potential energy. Last thing with energy, power. Power is a measure of the rate of energy use. Okay, measured in watts. And the way we find it is simply the work done over the time. So power is work over time. All right, just real quick, that's the unit there, watts, not work. That W is for watts. All right, moving on to momentum, the definition and the formula. Momentum is a measure of the, I always say, the amount of motion that an object has. Another way of thinking about it is who would win in a collision. The way we find momentum is simply mass times velocity. Okay. We talked about two important things with momentum. The first was impulse. So impulse is the change in momentum. Delta P. And conceptually, impulse tells us something very important. For a given collision, all right, so a given situation, maybe we have a person landing after jumping off of a box or something, a longer time leads to less force, and vice versa. All right, we have three ways of calculating impulse. Delta P is m delta V, and that just gets at the basic idea that impulse is the change in momentum. We can link it to force, average force specifically, so delta P is our average force times our change in time. And lastly, the third way here is that we can do the area on a force versus time graph. Okay, so conservation of momentum. Basic idea is if we assume no outside forces, then the total momentum of a system is conserved. This is really useful for collisions and explosions. So if you see problems with collisions or explosions on them, chances are that you're going to be using conservation of momentum. I'll say this again, this is a really important point. It's only conserved when there are no outside forces, and the only forces are no net outside forces. And the only forces are the forces within our system between the objects. Equation-wise, it's really not much. Pi equals Pf, initial momentum equals final. All right. We can transition this into 2D momentum, right? And in that case, we just look at our momentum in the x being conserved and our momentum in the y being conserved. Just like forces, momentum is a vector, and so we can split it up into x and y and do conservation of momentum in both directions. A few tips if we do have one of these, although you're probably just going to see this conceptually, but we're going to split velocity into x and y, okay, componentizing them, and you're basically going to do two separate setups. All right, last thing, this idea of elastic, inelastic collisions. Inelastic collisions means that only momentum is conserved if there are no outside forces. All right. By the way, if an object sticks together, that means for sure that it is inelastic. Okay, if it doesn't stick together, we still could have an inelastic collision, but if it sticks together, it has to be inelastic. Elastic collisions, on the other hand, mean that both momentum and energy are conserved. And this really is going to happen when we have a conservative force as the force between our two objects. So maybe we have a spring or we have magnets. All right, and that's going to lead to an elastic collision.